Hello, my name is Pedro Machado, and I'm presenting the PerceptionBlade project. I'm R&D manager at the Sundance Multiprocessor Technology. Sundance has been established in 1989 by Fleming Christensen. Since that moment, Sundance has been producing high-quality multiprocessor boards. In the recent years, we have been refocusing to acceleration, vision, sensor, and robotics. Today, we are going to look into the PerceptionBlade system, development tools, Edge AI, and use cases. The PerceptionBlade has four main models for input and output. As an input, we have the positioning and speed coming from GPS, IMU sensors, and encoders. We also have the vision devices interface that was specially designed to receive information coming from RGB, RGBD, hyperspectral, and multispectral cameras. We also have the actuators interfaces that allow us to interact with a wide range of actuators, in this case, the nozzles. We also have a cloud interface that allows us to exchange data securely using the protocols HTTPS and SFTP every time that the internet connection is detected. The information collected from the positioning and vision device are used for semantic segmentation, which means that the objects of interest will be classified and the group of pixels will be grouped and displayed on the image. Statistical analysis, for example, when it's desirable to estimate the number of fruits based on the sample collected through the cameras. Safety awareness for detecting humans and animals, and to stop the pulverizer every time that we have humans or animals within the range. Anomalies detection is used for the spotting anomalies in terms of the field. So for example, if a tree is missing, it will be important to let the farmer know that the tree is missing on a particular position. In this case, we'll be collecting the image and also the geolocalization. Vision speed estimation, as everyone is aware, when we are turning the speed, the angular speed has a variation. So for example, the inside will tend to have a bigger angular speed, while the outside will have a slower speed. And we want to make sure that we are pulverizing the same place just once. And this way, we can then adapt the nozzles according to the visual speed. The actuator controller is used to interface with the nozzle. So for example, in a situation where a human or an animal is detected, the actuator controller will tell the nozzle to stop spraying until the animal or the human is within the range. The semantic segmentation model is supported by the AI accelerator and the computer vision accelerator, both described on the field programmable gate array. The PerceptionBlade has the following characteristics: high performance using state-of-the-art Xilinx Zinc and PSoC, ideal for edge computer. Low power consumption, typically around 15 watts. Highly compatible with a wide range of commercially available sensors and actuators. Highly optimized for computer vision applications, embedded AI, and deep learning. Fully reconfigurable and expandable using PC104 form factor. Compatible with the most common Linux distributions, including Ubuntu, Debian, Red Hat, CentOS, etc. Software support for ROS and MQTT, Python and C++ support. The PerceptionBlade works on the top of the VCS1 hardware, which is equipped with ARM A53 CPUs that allow us to run distribution of Linux, for example, Ubuntu 16.04, 18.04, or 20.04. The VCS1 is supported by Xilinx VTs an unified software platform that delivers hardware-accelerated open source libraries that have been highly optimized for computer vision. We also offer MQTT compatibility, OpenCV, ROS, and ROS2, and Python on Zinc, or also known as PINK. All of this is supported by our SDK. The Xilinx Edge AI platform supports a number of industry standard frameworks, including TensorFlow from Google, Caffe from Berkeley, Darknet by Joseph Redmond, and Carrot, which is a high-level neural network API written in Python and capable of running on the top of TensorFlow. Here are some examples of the applications that we have been testing the system. Sundance has partnered up with several universities using the Sundance university program. Here we can see a student that had as his final year project autonomous navigation. We can see here a very simple SLAM map, and the student on the corner is moving the target, and we have the robotic robot wheel that will move towards the target. We also have partnerships with Fraunhofer. Here we can see a real-time disparity estimation running on the VCS1 system. It's composed by 2 cameras and our platform. Here are the examples, which are very impressive. As you can see, this is being processed in real time. Here we have an example on how we plan to control the nozzles array. In this example, we have 10 groups of nozzles, and the information is being captured by the opposite camera, which is an Intel CSD435, and you can see the green zones being switching on and off, which will that represents the sections of the nozzles that will be activated in this situation. Another example is the dynamic frame rate. Here, what we are doing is to fix a position, and we are following that position. As you can see, when the image stops, the position on the screen also stops. And this is what allows us to have control over the nozzles and the reduce of amount of spraying, and avoid situation where we are spraying the same places twice. Here is another example where we are going to classify images in real time. Here you can see that sometimes on the right-hand side, the source code stops. And the reason for this is because the FPGA is capable to classify the object on the scene faster than the GPU to process the same information on the screen. We also have a video, and here you can see that the cards are being processed, are being classified, and this is being processed in real time. Another application is UAV obstacle avoidance using the Tulip platform. Here we can see the VCS1 system being used to control a drone. So this is the information that is being processed while the drone is moving. And the information is being used to allow the drone to autonomously move, avoiding the collisions. Here, we see another project where the VCS1 is controlling an autonomous robot that goes through the vineyards to collect information and compute the NDVI of the leaves. As you can see, the robot is navigating autonomously. Here is another example where we are looking into the model that detects animals and people, so that that information can then be used to prevent the system to spray animals and people that are close to the sprayer. Here is another example of a final year student currently working for Sundance, where you use the system to compute the NDVI and to classify the trees. So every time that leaves are detected, it will compute automatically the NDVI. Here is another application where we see the process of training. Here, you'll be able to see how important data is, and also the time why justification why it takes so long to train the neural network to be able to detect trees. So, for example, when you have 400 iterations, you are almost unable to detect most of the trees. When the number increases, you'll see that the algorithm starts to generalize and starts to be more accurate when detecting. Okay, as a conclusion, Sundance PerceptionBlade system delivers the desirable heterogeneous computing facility for edge computing. More details about the PerceptionBlade, also known as ICS1 and also ICS, can be found in the following book. This book has been published this year in 2000. It's called Towards a Ubiquitous Low Power Image Processing Platform. In that book, you'll be able to see how you can use the VCS1's hardware and also the ICS. Sundance is a Xilinx Alliance member, and PerceptionBlade is highlighted on the Xilinx AI blog. We are leaving here the URL so that you can visit. Please. Thank you for watching our presentation. I hope you enjoy it, and we are looking forward to know the result of our application. Thank you.